Hi everyone, my name is Michael Brett. I'm a Principal Specialist for Quantum Computing at AWS and part of the High Performance Computing go-to-market team. Today, I'm excited to share with you one of the new technology areas in the cloud with this session entitled A Sneak Peek into the Future with Quantum Computing. Before we dive in, let me walk you through what you can expect from today's session. First, I'll give you an overview of quantum computing as a technology and why we're so excited about its potential at AWS. Next, I will introduce Amazon Bracket, our quantum computing service, and explain a little about how to get started with quantum computing in the cloud. And finally, I will hand over to one of our customers, Joe Fitzsimons from Horizon Quantum Computing, who will talk you through a tool chain that they're building for transforming your existing classical code to work on a quantum computer. Quantum computers are a fundamentally different type of computer to what you're used to. If you look down at the behavior of the very, very small, down at the atomic scale, then a different kind of physics starts to emerge, quantum physics. So what if we could build a system that could control information at this physical level and do computational work? Well, this is what a quantum computer is. And with a different kind of physics, it means we can do a different kind of math, and a different kind of math means a different kind of algorithm, and a different kind of algorithm means we can solve problems in a totally unique way. So let's take a look at what I mean by quantum information. Quantum bits, or qubits, are the fundamental units of information in quantum information processing, in much the same way that bits are the fundamental units in classical computing. Classical bits can only be in one of two possible states, either a 0 or a 1, like a light switch being either on or off. Qubits, on the other hand, can access a much larger space in 3 dimensions. Think of a really fancy dimmer switch that can operate in any state between on or off, but also change the color of the bulb. It can occupy any point on a sphere. It's helpful to think of this state between 0 and 1 as a kind of probability distribution. When a qubit is measured, it will resolve to being more likely 0 or 1, depending on the probability characteristics at the time. And just as there are many ways to realize classical bits physically, whether they're voltage levels, lights on or off, or switches, there are also many ways to realize quantum bits, including atoms, electromagnetic loops, and photons. So now that we have a qubit, let's take a look how we can manipulate this building block of quantum information physically. So just like in classical computing, where we can change the state, switching on or off, by applying some electromagnetic pulse or current, the same is true for quantum computing. Here we have 2 qubits on the screen, and we can physically apply a current via a control circuit that changes the information in that qubit. So let's apply a single pulse via the qubit control circuit and affect the bottom qubit. Here the pulses move the qubit from the north pole, effectively 0, now into a state of superposition, something between 0 and 1. Next, we can manipulate 2 qubits at once. Here the qubit controller is sending a pulse down the center line, and we're manipulating the bottom qubit's information based on the condition of the top qubit. The change is a conditional one. We're changing the state of one qubit based upon the state of another. As programmers on classical computers, we don't really think about the physical circuitry that often, and the same is true for programming a quantum computer. So instead of electromagnetic pulses on wires, we can instead represent all of the physical interactions with a series of gates. So think of these gates as like reading sheet music from left to right. As each qubit is a line, and as time progresses, we apply gates in building order, building up transformations that create an algorithm. The circuit description is then just assembling many of these gates together to perform the desired algorithm. So in our example case here on the screen, we have 2 qubits, and we've performed first a Hadamard gate, a single qubit gate operation that's put the bottom qubit into a state of superposition. And next we've performed a CNOT gate, a conditional NOT gate, a type of controlled gate where the rotation of the target qubit depends on the state of the control qubit. So in quantum computing we have a diverse set of gates just like these we can arrange over time to perform some really complicated algorithms. So with this unique and different kind of computational tool in our toolbox, what problems can we take on? Well, there are many problems for which classical computers are really well suited. And that's the blue circle in the middle of this screen. Quantum computing won't replace these at all, and you will continue to use classical computers, including CPUs and GPUs and cloud services like AWS, to solve your problems. And the grey box around the outside represents all the really tough problems in the universe, including those described by complexity theorists as NP-complete problems. These problems are just as tough for quantum computers as they are for classical. But there exists a set of problems in the center that are very challenging for a classical computer, but can be solved with a quantum computer much more easily. And so this is the area that we're looking in right now. We're trying to find the problems that are best suited to a quantum computer that we can't solve with a classical. But how much better could quantum be than classical for these kind of problems? Well, the truth is we don't really know yet, and this is the holy grail of quantum. We're building the systems and we're experimenting so that we can find solutions where a quantum computer can radically outperform a classical computer. There's a lot of space to explore too. There are many, many problems for which the classical solution becomes increasingly more difficult to solve as the problem size increases. So this is our call to action for you as developers. If you're interested in solving really tough problems, quantum computing has the potential to unlock a new set of algorithms so that we've got a new tool in the toolbox and to take these on. So with that background in quantum computing generally, let's now turn to what AWS is doing to bring quantum computing to the cloud and enable our customers to explore this technology. At AWS, there are 3 pillars to our approach to quantum computing. First, we have Amazon Braket, a fully integrated AWS service in the cloud that lets you design, test, and run quantum solutions. We also have our Quantum Solutions Lab, a professional services team of quantum computing experts with whom you can partner on conceiving, building, and testing applications or taking on tough research questions. And third, we have our AWS Center for Quantum Computing, a new academic research institute based at Caltech with a mandate to research algorithms, quantum error correction, and hardware. So a little more about Amazon Braket then. Braket is a fully managed service that makes it easy to get started with quantum computing. We provide a fully managed development environment based on Jupyter notebooks that comes pre-configured with a suite of software tools, including our own SDK. The Amazon Braket SDK is a hardware-agnostic programming framework for quantum computing that allows you to access a range of technologies all through a unified framework. By working in the SDK, you can build, test, and fine-tune your own quantum algorithms or build on a wide range of pre-built examples. We also provide access to a fully managed circuit simulators in the cloud that are parallelizable, cost-effective, and always available. And, most importantly, we provide secure, on-demand access to a range of quantum computers, and I'll talk more about those in detail in a second. So here on this slide, you can see the architecture diagram for Braket. Braket is fully integrated into AWS to provide user access management, security, logging, monitoring, and more, so you can manage all of your quantum computing resources just like you would any other service on AWS. And users can access the service via managed notebooks, their favorite IDE, or the Braket console. And we have high-performance simulators running in the cloud, plus 3 hardware backends. So onto hardware. Today we provide access to 3 different kinds of quantum computers with 3 different modalities. We have superconducting qubits from Rigetti, ion-trap computers from IonQ, and quantum annealers from D-Wave. Having a diversity of quantum processors on Braket allows you to explore the differences between 3 very different types of quantum computers, all in the same environment. And in the fullness of time, you can expect that we will add more computers and more diversity of computers from the quantum computing ecosystem onto Amazon Braket. The pricing on Braket is transparent and has a consistent structure across all the hardware platforms. And most importantly, Braket users only pay for what they use. There's no upfront commitment or minimum spend. The pricing is based on a per task price for each job that's sent to the quantum processor. And then for variational algorithms with many loops through each processor, another small charge for each loop that algorithm goes through. I've also mentioned 2 high-performance simulators that allow you to test your algorithms at low cost before you deploy to the hardware. We have SV1, our state vector simulator, running on EC2. This is a quantum circuit simulator which can do up to 34 qubits. We also have TN1, our tensor network simulator, running on GPUs, and it can run quantum circuits up to 50 qubits. So we've talked a lot about hardware so far, but Braket also includes some powerful software tools. At reInvent in December, we introduced Pennylane. Pennylane is an open source software library that brings machine learning tools to quantum computing. It allows you to use familiar machine learning libraries such as PyTorch and TensorFlow to program quantum algorithms and make it easy and intuitive to get started with hybrid quantum computing. Pennylane comes pre-installed with the Amazon Braket SDK and notebooks, and we have a number of tutorials for you to get started with. We provide access to application libraries for chemistry, optimization, and machine learning. Pennylane on Amazon Braket is optimized to train models up to 10 times faster when you use the Amazon Braket simulators based on their ability to parallelize the circuit executions. As you get started with Braket, I wanted to leave you with a few best practice tips from our team for getting the most out of the system today. Firstly, you should recognize that each different computer natively supports different gates. You can optimize your circuit to reduce the number of operations needed by focusing on the native gates for each computer. For example, a controlled phase gate or CZ gate on Rigetti, or the Molnar-Sorensen MS gates on IonQ. Then, choose a QPU that matches best to your circuit connectivity. This will reduce the overhead of having to perform additional transformations in your gate model that uses up valuable processing time. You should also choose the number of shots to match the measurement accuracy so that you complete the number of loops that you need to converge on a solution. But you should also set a maximum number of iterations in hybrid algorithms to avoid getting stuck in essentially an infinite loop scenario for non-convergent applications. So it's like setting a floor and a ceiling for the number of tasks that you want to send to the quantum computer. So looking back at what we offer via Braket, we've got a hardware-agnostic quantum computing platform with end-to-end integration with the rest of the AWS cloud services. We also offer scalable circuit simulators in the AWS cloud, and you only pay for the resources that you use. This is an excellent tool for getting started in quantum computing. So now I'll hand over to one of our customers, Joe Fitzsimons at Horizon Quantum Computing. You will have seen from my presentation today that quantum computing can be a little complex to adapt to quickly. And that's why companies like Horizon are building tools to help developers abstract away that complexity from the lower level circuit diagrams and provide software tools for developers to readily adopt quantum computers and the hardware that's needed to solve business relevant problems. So over to you, Joe.
Thanks, Michael. I'm Joe Fitzsimons, founder and CEO of Horizon Quantum Computing. Quantum computing faces two main challenges. First, developing hardware capable of implementing quantum computation on a large number of qubits with low error rates. But also, developing tools and techniques to allow users to take advantage of that hardware to solve business-relevant problems. The second challenge arises because quantum computing works in a non-intuitive way, making quantum algorithms hard to develop. Furthermore, there's a diverse range of quantum hardware in development, and overcoming noise often requires writing code specifically tailored to a given processor. This renders the code non-portable. Quantum computing also lacks abstraction, meaning that programming languages often require building up circuits gate by gate, making many users reliant on libraries, which limits the domains to which quantum computing is applicable. But imagine if things were different. Imagine if you could program a quantum computer just as you program a laptop or workstation. Imagine abstracting away the quantum computational model, allowing domain experts in diverse sectors such as energy, engineering, pharma, and finance to take advantage of quantum processing in their code, without having to develop or outsource quantum expertise. Imagine being able to write code that's fast and efficient on classical hardware, but that gets even faster on quantum hardware. It is portable to any technology. At Horizon, we're working to make this a reality. We're developing a complete code, compile, deploy system for quantum applications that abstracts away the details of quantum computing, allowing users to accelerate code written in conventional programming languages such as MATLAB and Python. Our users can provide classical code. We handle the process of compiling it into a quantum program to run on particular hardware. To the users, it looks like their code has simply been deployed as an API. We're building a full toolchain for going from classical code to deployed quantum application. Users can work at whatever level of abstraction is right for them. If they start from classical code, then we break it apart, refactoring it and simplifying the features that make the code slow, loops, recursion, and operations with high implicit cost. We break loops and recursive function calls apart into simpler units, and then classify each, identifying opportunities for quantum speedup. This allows us to construct a quantum algorithm for the task. From that, we can construct a concrete set of quantum circuits and flow control using an optimizing compiler. We automatically adapt these circuits to the constraints of the target chip, respecting nearest neighbor connectivity and converting to the appropriate instruction set for the chip. Once the computation is ready to run on hardware, we allow it to be called via an API with any desired input. So what does this classical to quantum process look like? Here's some sample MATLAB code implementing a global optimization algorithm. First, our system eliminates intermediate variables. It removes operations not affecting the outcome. Now it can split the inner loop into independent parts. Again, assignments not affecting the output are removed. And now the redundant control flow is also removed. Loops are recognized and replaced by special functions. Again, operations not affecting the outcome are removed, and redundant control flow is removed. Intermediate variables are eliminated, and the outer loop can now be split. The for loop is removed through simplification, and the intermediate variables are removed. The loop can now be replaced by a special function. Finally, there is some cleanup, removing intermediate variables again. Lastly, subroutines which can be sped up quantum mechanically are identified. Here, this results in an exponential speedup of the classical algorithm. Our compiler is structured in layers, each offering an increasing level of abstraction. Hydrogen handles gate and pulse level instructions. Helium adds basic-like flow control, leading to a Turing-complete quantum programming language. Beryllium adds further layers of abstraction and adds object-oriented programming features. Finally, carbon abstracts away the quantum mechanics entirely, allowing users to program with conventional code. Users can run carbon directly on classical hardware, or can compile down and run on quantum hardware, or in simulation. We're building with Amazon Bracket as it allows us to access quantum hardware in a cost-effective manner, allowing us to scale our capacity as our user base grows, without the high upfront capital commitments of other hardware access models. The AWS ecosystem also allows for tight integration with classical systems, allowing us to run simulations either via Bracket simulators or via custom simulators deployed on EC2. EC2 is also the clear choice for classical code evaluation on multi-core and GPU systems and clusters. As of today, we've built in the capability to output code for Amazon Bracket and to run our first tests on IonQ hardware. Soon we'll be allowing users to compile and deploy quantum applications using AWS backends. In the future, we'll be offering users the ability to automatically divide tasks across CPU, GPU, FPGA, and quantum resources, powered by AWS.
Well, thanks, Joe. That was a great example of how the abstraction layers from the qubits are being built up to make it easier and easier for developers to understand. So to wrap up, there are 3 key takeaways from this presentation. Amazon Bracket is available today to enable you to start exploring quantum computing. Machine learning, using tools like Pennylane, is one of the most promising application areas for customers, and tools like Pennylane make it easy to build and get started with this new technology. Finally, customers and partners are building even more tools to help integrate quantum computing into existing workloads and abstract away some of that complexity so that we can connect the quantum classical hybrid workloads of the future. So thank you for attending today's session. We're excited to see what you can build with Bracket and AWS.